silicon is an important semiconductor of both fundamental and technological interest. We recently showed that a well-ordered cubic Charles mesophase of all germanium semiconductors, NSU-GE1, can be synthesized. This mesostructure could not be rendered porous because entrance to remove the surfactant caused the framework to collapse, partly due to its very thin walls, approximately 1 nanometer. Now we go to the main content. It is divided into two parts. Part 1, we will tell you about how to make a Germany, and part 2, it refers to Germany's potentiality. First of all, we go to learn about the way how to Germany is making up in our life. Here, we describe a different synthesis strategy that leads to mesoporous germanium with very high internal surface area. This mesoporous germanium and NSU-GE2 exhibits a considerably blue-shifted energy gap relative to the Phuong germanium as well as photoluminescence. Besides, a family of mesoporous germanium semiconductors were repaired with the use of templating GE polymerization by liquid crystalline phase according to the metathesis reaction of EQ1, namely linking GE9 cultures in formalin solution with germanium tetrachloride in the presence of cell assembled surfactant, resulting in formation of a well-ordered mesostructure. Luckily, the surfactant creates an organically autotropic liquid crystalline phase to template the inorganic GE framework. Now we look at the reaction on the screen. These manuscripts were under review. The preparation of a mesoporous germanium with hexagonal pore symmetry was reported. In order to understand specifically, let's find out the origin of germanium. Material was prepared from the oxidative coupling of polymeric, especially without a linking ion. The chemical composition of the product as determined by elemental carbon, hydrogen, and nitrogen, and thermogravimetric analysis (TGA). The purity of the inorganic framework was confirmed by energy density spectroscopy (EDS), where only GE element was observed. As you can see, potassium or halide ions were not detected, suggesting a complete metathesis of all germanium and chloride bonds. On the other hand, surfactant removal was achieved by a two-step ion exchange thermal approach. First, the surfactants were pre-played with ammonium nitrate. The successful incorporation of ammonium cation inside the GE framework was confirmed with elemental carbon, hydrogen, and nitrogen analysis, and Fourier transform infrared spectroscopy, which show characteristics and an absorption bands at 1,420 reciprocal centimeter, as you can see in the picture. The subsequent removal of the ammonium cation from the mesopores were achieved with mild heating to give hexagonal amorphous GE with very high mesoporosity.
After the thermal treatment to remove the ammonium ions, STIR spectroscopy showed the presence of germanium hydrogen as strategic bands at 2141 and 2011 reciprocal centimeters without the characteristic of nitrogen-hydrogen banding band, as you can see in the figure 1C. This suggests that the removal of ammonium ions was in the form of volatile ammonia molecules, whereas the hydrogen ions transferred to the germanium framework to produce the germanium-hydrogen bonds activating the surface.
Additionally, temperature also has an effect on the process. Thermogravimetric analysis provides of and repair NSUGE2 materials show a weight loss of 5.4% below 210 degrees. Between 210 and 580 degrees, a gradual weight loss of 28.2% is observed, which is attributed to the decomposition of the surfactant. The inorganic residue and sequences of points and repair and template remove materials were primarily crystalline GE. The formation of elemental GE supports the notion that framework in NSUGE2 is in fact reduced.
The long-range periodicity of the bond structures of S repair and SU germanium-2 and template removed material was confirmed with powder X-ray diffraction (XRD) and transmission electron microscopy (TEM). The XRD patterns exhibit a strong peak at low scattering angles to theta less than 3 degrees and a very quick filter at 2 theta similar to 4 degrees, which could be attributed to hexagonal B6 mm symmetry, as you can see in figure 1b. The d-spacing of the first strong reflection gives a pore periodicity of 4.8 and 4.6 nanometers, respectively, for S repair and SU germanium-2, which contain its surfactant and template removed material. The absence of red reflection at high angles to theta greater than 10 degrees in the XRD pattern indicates the aperiodic nature of the inorganic framework and the absence of crystalline germanium impurity. The corresponding fast Fourier transform FFT patterns of S repair and SU germanium-2 and template removal mesoporous germanium are depicted in figure 2.
The TEM and FFT analysis confirmed the presence of well-defined long-range hexagonal arrangement of pore channel in the S repair material, as you can see in the picture 2A and B. The image also confirmed that hexagonal pore ordering is retained even after ammonium ion exchange and heat treatment of the sample, as you can see in the picture 2C and D. TEM analysis indicates average pore prediction of 4 and 3.8 nanometer and pore diameters of 2.3 and 2 nanometer respectively. This gives a framework word thickness of 1.8 nanometer. germanium is coupled with carbon and silicon, so it has many physical and chemical properties as carbon and silicon that make for the application of it almost the same element in the 4A. Germanium resembles silicon that is semiconductor, so it is widely used in engineering. So morphology hexagonal mesoporous germanium of germanium can synthesize microfields for high-performance lithium-ion and sodium-ion battery anodes. Also, researchers are testing into solar battery application and electric devices. Germanium resembles carbon that has high absorption properties. Therefore, hexagonal mesoporous germanium is widely used in absorption. Nowadays, infrared IR spectroscopy includes measuring encrustment made by germanium. Also, it is used for separation and magnetization in chemistry industry. Hexagonal mesoporous germanium is a good catalyst for noble metals, metal oxide, and metal complexing reactions. In addition, it is also an environmental catalyst used in wastewater treatment industry. It has many important applications in biology, such as cell maker, drug delivery, gene delivery, bone regeneration, and stem cell checker. It is the end of our representation. Thanks for your listening.